then follow directions here and you'll be fine. All right, here we go. Okay, with your partner right here, we're going to discuss. Instead of writing things down, you're just going to have a conversation with them. Okay, and I'm going to try to overhear as many conversations as possible about, okay, what the transformations occurring here. Person number 1, call yourself partner A. Person number 2, call yourself partner B. Person A. Okay. You, Doug, you, Ben, you guys can move together here. Does anybody else need a partner that we have? Okay, partner A. Okay, you go ahead and tell them right now what transformation is occurring.
Well, that is
Okay, I heard a vertical stretch of 2. Okay, person B. Okay, go ahead and discuss with them. Okay, what happened to this parent function? Okay, we did here. Now, this right here, does that change what you say? If I put the parentheses around that like that, that is telling me that I have a horizontal, okay, stretch occurring here. This is a horizontal stretch of 7/2 because you have to flip it over. 7/2 is bigger than 1, same as a stretch. Okay, however, without those parentheses right there, okay, 2 things occurred. Okay, 1, it was a reflection. I heard somebody say flip over. It's a reflection. That's the transformation that occurred. A reflection over the x-axis, okay, and then we are vertically, okay, compressing it by 2 seconds. Okay, partner A, we're back to you. What's happening there? Alright, that's quick. Translate up 2 units. Not move up 2. Not shift up 2. Translation of 2 units up. Person B, go ahead. Alright, not move down, but translate it down 4 units and vertically stretched, okay, by 2. Is this who we on, partner B or partner A? Partner A. Is that the same thing? Okay, now your discussion needs to occur. How did I change it from this to that? Well, it's still translated down 4. Okay, but I heard this is now a horizontal. Is it a stretch or a compression? Now, you don't see the 2 as a stretch because it really comes as its reciprocal of a 1/2. So a horizontal, a 1/2 is a compression. Horizontal compression of 1/2. Okay? All right? Next person, go ahead. Discussion right there. What's occurring in this transformation? To the parent function f of x equals x squared. Alright, 3 things occurred. I heard translate up to. I heard that was up to. Reflected over the x-axis. Now the question is this vertical or is this a horizontal?
vertical.
Okay, vertical because it is multiplying the whole function, the whole parent function right here. Okay, so this is the same as 3/8 times this, okay, function right here. The parent function is x squared. So you're timesing that parent function by 3/8, and that times the y's, and the y is the vertical. So yes, you are correct. This is a vertical compression. Okay, vertically compressing it this way. Okay, by 3/8. Okay. Next person, you have to tell me what transformation has occurred here, and then tell them where that vertex is going to be located. guys put the vertex at 2, 3?
No.
But I have 2 and 3 there. Okay, in vertex form. Vertex form is this right here. We'll talk about different forms later. Okay, but the vertex is located, okay, at H and K. Okay, but you have to set that x plus 2 equal to 0, and this actually moves it, okay, left 2. So that should have been negative 2, telling me that this part right here was translated up 3, but that right there is moving left 2. So translated up 2 and to the left, or sorry, up 3 to the left 2. All right, next person. Your discussion. What's occurring in this function? Translated up 6. Left 1. Reflected over the x-axis. Vertically stretched by a factor of 4. All right, next one, you're up.
And it goes up, but when I goes
All right, we have translated that thing. Out 5. You could have on this one got away with talking about the stretch or compression factor first. Okay, but this I like to talk about your translations. Up 5. Okay, then since this right here is working inside the parentheses only on the x function, this is horizontal. And horizontals always have to be the reciprocal. So the reciprocal of 1/16 is 16. 16 is greater than 1, telling me it's a stretch. So horizontal stretch of 16. Okay, with that translated up 5 units. All right, next one, add a little bit more. Go.
Translated left by 1.
Sydney.
Yeah, the rich is going
Quit screwing around.
Okay.
All right, translated up 6 to the left. 1 and vertically compressed by 2/5. That's the last one.
So it's going to come down. Yeah.
Horizontal.
and
Later on, I'm going to get some of you on this one right here, so pay close attention. This is why I leave parentheses around this, and I do not distribute in, okay, because this right here tells me right away, the x minus 2. That's translated right 2. Okay, the minus 1 translated down 1. Okay, but this 3/4, okay, is acting, it's going to be squared, it's acting on just this x. So it's a horizontal, okay, compression or stretch. And since it's a horizontal movement here, it's horizontally going to be, okay, flip it, 4/3. 4/3 is bigger than 1, so that's a stretch. Horizontal stretch of 4/3 with a translation right 2 and down 1. Okay? Now, the one thing you guys got to realize is horizontal stretches and compressions. Okay? I will talk about this later, I think. It'll be better when you see the words. Okay, on your whiteboard. Okay, now you're individually just going to be doing this. I just want you to flip up the answer. Okay, if the parent function, and last hour didn't realize I was writing the parent function down every time. F of x equals x squared. Okay, if it is vertically stretched by a factor of 2 and shifted up 8 units, what's the equation of the new function? Your homework assignment tonight is going to have something just like this, but they're going to have this parent function like this all inserted in here. Okay, so don't freak out when he says reflect f of x equals x squared. Okay, give me the formula. Flip it up. Whatever you think you're going to get. Good, good. No. Yes. Got your answer? Flip it up. Yes. 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 No. No. Yes. Yes. Yeah, it is. Yes. Okay, if you're going to take this function right here and stretch it, if I vertically stretch something, I have to take the function itself and multiply it by 2. Okay, that takes this parent function of x squared times it by 2. Okay, then I have to shift it up 8 units. Okay, so I have the up 8 units and vertically stretching it by a factor of 2. Okay? Alright, erase your boards, and here you go. Next one. Same parent function. This time I wrote it y equals. You can do the same thing. You can call it f, you can call it h, call it whatever you want. Take that parent function, f of x equals x squared. Okay, and we're going to reflect it across the x-axis, vertically stretch it by a factor of 4, and then shift it right 2 units. What's the equation of the new function? You're close, Anastasia. Stasia, right? Did I say it wrong again, or did I say it right? I didn't?
Nope.
Say it again for me. How do you say it?
Anastasia.
Stasia?
Sia.
Stasia.
Sia.
I don't know.
Like the
Sia? Say the Sia there?
Sia.
Sia? Okay.
Anastasia.
No. No. Yes. Yes. No. Yes. Yes.
Yes.
Yes. Yes. Let me see, Abby. Yep. 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 All right. To take this function, first of all, some of you are writing f of x. Okay, your f of x is already your original function. Okay, so if we're going to write a new function, you need to assign it to a different variable. Okay, we're going to reflect it across the x-axis. Okay, shift it right 2 and stretch it vertically. Okay, so if I'm going to shift it right 2, okay, this part right here has to shift right 2. If I'm going to stretch it vertically, I got to multiply that whole parent function by 4. And if I'm going to flip it over the x-axis, okay, I need that minus sign. Okay? Alright. The parent function. Okay, we'll put this one right over here. I'll call it g of x this time. Okay, if the parent function to the left is reflected across the x-axis, vertically compressed by a factor of 1/4, shift it to the right 2 units. Okay, what is the new function going to be? Nope. Yes. Nope. 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 It is shifted to the right 2, not a half.
Oh.
How much is that shifted by right there? It is shifted to the right 2. This is shifting it to the right 1/2.
Forgot this. Woohoo!
No. I like it.
That's the one.
All right, guys. This is where I said your orders of operations. I always talked about why should we do the translation factors first? Because right here. Sometimes it matters, and sometimes it doesn't. This is one case right here where it's going to be helpful to talk about the translation. X right minus 2. Put parentheses. Okay? The next factor right here. Okay? This is horizontally compressed. So automatically, I know I'm going to take this x function right here, this x variable, okay, and multiply it by that horizontal compression factor. And since it's 1/4, I got to multiply that x, which is being shifted right, by 4. Okay? This is what's being squared. Okay? Do I put the negative right there on that 4 because it's reflected over the x-axis? Because what happens when you square -4? And now there's no reflection, or there's no reflection occurring there. Okay, so instead of putting it there, you got to put it on the outside. Okay, so here we have h of x, okay, equals, okay, this negative, okay, of 4 times x minus 2, okay, that quantity squared. Questions there on that one? Alright, just to let you guys know, this is where I wanted you to go, verbally understand it, because I think we're on to something else here. Okay, if I'm looking at this right up here, I need your thinking caps on right now, because this is all going to be verbal. If I horizontally stretch something, is that the same thing as a vertical compression?
Yeah.
Horizontal stretch,
On a
vertical compression.
Yes. On a graph.
On a graph they are. Okay? You're going to, if you look at this function that I have, okay, behind me right here. If I was to draw this out this way, is this thing being horizontally stretched or is it being vertically compressed? Do you know unless you see the numbers in the formula? I could be saying I'm horizontally stretching this. I could also be saying I'm vertically compressing it. Okay, what you need to realize is, Algebra 2, you don't do a lot of horizontal compressions or stretches. The reason you don't is because of what we just talked about right here. If there's a negative inside and it's -4, we end up squaring it all out. Okay, and a great example is one we did here back this way. Okay, this problem right here. If I come over here and I was write that function up there like this, and I put it like this, typically in Algebra 2, we're not going to talk about graphing, okay, a -3/8, okay, a horizontal stretch of 3/8. What we're going to do is we're going to change this and say, oh, this right here, it's easier to draw myself, okay, a vertical compression of 9/64. Why I'm talking about it now? When we get to trigonometry and pre-calc and calculus, I need you to understand, okay, that when I'm coming up here and it's not doing what I want, come on. it's not doing this right now, but I was able to compress this thing before. I don't know what the properties are. Do it up here. Let's draw it down here. What have I done there in green to that function right there? Haven't I kind of smushed it in horizontally? That's a compression. You talk a lot about the sine curves, okay, and the cosine curves, okay, about how they're going to be compressed or stretched. You guys remember sine, cosine, and tangent from last year, correct? Okay, we didn't talk about, okay, when we're talking about graphing the actual function, okay, like we graph lines, like we graph parabolas, we can also graph the sine function and the cosine function, and they're going to see horizontal compressions, okay, a lot more in pre-calc. Okay, but in Algebra 2, a lot of times your vertical, here's your thinking cap again, hear me again, your horizontal stretch, my finger's on it right now, this is a horizontal stretch, this right here is a vertical compression. We're going to talk about the vertical compression a lot more than we're going to talk about a horizontal stretch. Okay, it's just going to work a lot better in graphing. Okay, if they're always the vertical ones. Okay, but I didn't want to just do those because there's times that you're going to need to know about the horizontal stretches and compressions as well. All right, here we go. Just a little bit of video here about applications of stretches and compressions and translations. Okay, by the Professor Berger.
You know, it's always fun to take a penny and just sort of drop it into a wishing well and make a wish and say, you know, I wish I could do math all the time and never do anything else. And then hopefully one day your wish might come true. But there's a question about, well, how fast will that...
I am going to warn you here first, okay? His play on words, okay, is, I think, probably on purpose. But, yes, you're going to giggle with what he says, okay? But in the process, do not get lost in what he's teaching you. Okay? He has a worse sense of humor than I do. Okay, so that's
penny fall when you drop it? Well, it really actually depends upon the force of gravity. Now, on Earth, okay, we know the force of gravity here, but in fact there are other planets, and the other planets turn to have different forces of gravity. So here's some basic information that I want to share with you. So the distance d in meters that a penny has fallen in a wishing well is given by the equation d equals negative g times t squared, where g is the force of gravity in meters per second squared, and t is the time in seconds that the penny has fallen. And now, what we want to do is to use the chart to write equations for a penny falling on Mars and a penny falling on Uranus. So, here are all the different gravitational constants for all the planets. You can see Mercury, Venus, you can see Mars, and you can see Uranus. So, the question is, what is the formula? Well, I'm going to show you. Because all you've got to do is take the formula that we're given, that function, d, which really depends upon t. And for Mars, which is the first one, you see the gravitational constant is 3.75, so it's negative, by the way, sorry, so negative that, negative t squared, that's for Mars. And what about Uranus?
Nice thing about this,
Well, then the function would look like this.
His graphics and everything.
Negative 10.5. Notice that there's the gravitational pull on Uranus is actually greater than Mars.
He'll pop up the graph.
Okay,
the two
and so
graphs
now,
in a little bit.
those are the functions, and the question is, well, what's the difference between them? Well, you'll notice that there's a change in what? In the vertical shift. That's only a vertical shift here. Both of these are representing parabolas that are sad-faced parabolas, but this constant of gravitational pull depends how tight or how sort of wide it is. And you can see in both cases, these are sort of reasonably big numbers. They are, remember, the parabolas are going down, but you can see that the gravitational pull on Uranus is actually greater than that on Mars. And so, in fact, we see that there's more gravity in some sense. The penny would actually drop a lot faster on Uranus than it would on Mars. And so there you see it. You can actually use the parabolas and their translations, in particular vertical shifts and vertical stretches, to actually even analyze different gravitational poles on different planets. Pretty cool stuff. I'll see you soon.
Pretty cool. I'll use him occasionally on different applications. Okay, that are up there. Okay. All right. We got one last thing here that we're going to talk about, and then we'll get to our homework assignment here. Okay. Our last form. When we talk about linear graphs, we had 3 equations that we wrote down for lines. One of them was
In your phone.
standard form. Go ahead and write that down on your sheet, on your little whiteboard.
Just the words.
No, the formula you use for standard form. Okay, the other one. What's another one we had? Point slope. Go ahead and write that formula down. Standard form.
Do that.
Point slope. And what's our last one?
Slope intercept.
Okay, slope intercept. And what we learned is there was a purpose for using slope intercept form versus using standard form. Slope intercept form, if we were given the y-intercept, we put it in slope intercept form. Okay, if we were given a slope and a point on the line, we chose to use point slope form. Okay, the standard form is, just something that we wanted to clean things up and make it look nice and neat. Okay, they use that standard form. Okay, we didn't use it a lot in graphing. Okay, we just used it to simplify things. Well, we're going to do the same thing for quadratics. There's going to be 3 forms. There's going to be a standard form. Does anybody know what that looks like? If you do, write it down on your board and flip it up to me. What does standard form look like for quadratics? You've had quadratics in Algebra 1.
I had a really.
Great teacher. Okay, so I will send this to them and say that you said they were great. Okay.
I don't care.
Whoops. Okay, quadratic. Okay, you don't need those capitals, though you won't see them as much.
Oh, I see.
Okay, that's standard form. Have you guys ever factored a formula like this before? Oh, yeah, well, we might have done that once last year. Okay, so you may not have seen it like this right here written, x minus p, x minus q, but this is called intercept form, and they had an A out in front talking about, its compression or stretch factor. And then our last one, so we had standard, we had intercept, and our last one we're going to talk about today, okay, is vertex form. We've been doing vertex form, I've been talking about vertex form. You guys have been writing down the equations of these things in vertex form. In function notation, it looked like this. We should know what the H and the K stand for, right?
I sure do.
You should, right? That's the vertex. And we should know what that A stands for. Now, it's not really slope. I don't need you walking into Mr. Beal's class next year and saying, Mr. Johnson said it was slope. Because if we had a slope right here of 3/4, that means this would go down 3 over 4, down 3 over 4, and this graph would end up being a line. The only reason I talked about this as slope, because that's something we could connect with width. This A really is going to be the vertical stretch or compression factor. Okay, making this parabola wide or skinny. What we have to find out here is, if I give you this equation like this, what is, or I should say I give you this graph, what's the equation of it? Anything you could plug into this formula right here? Okay, go ahead and do that. Write it down on your board. Plug the vertex in. Plug it in. Okay, we should have f of x equals a times x minus k 20 squared plus 3.
That's what I got.
All right, now, this f of x is really the y component, correct? How many points are on a function? Infinite. How many points did I give you on this function right now?
No, 2.
2. How many of them have you used so far? 1. Okay, we need to use that other point. There's an infinite number of points you could use, but I gave you one of them, 3, 0. And that one point is going to help you find the slope. Very similar to how you did with, lines, y minus y over x minus x. But instead of doing that, we're going to take, and do you see what x and y there are? They stand for a point on that function. Any point on that function. All you need to do is plug in any point on that function, and you should be able to find, that a factor. Go ahead and do that. Plug in the point that you have, 3, 0, into your function. Make sure you plug the x into the x and the y into the y, because it's very easy to say 3 in for y and 0 in for x. That's not true. The x factor, is 3. The y is 0. So your substitution should look like that right there. Okay, I substitute 3 in here, and then words of operations. Just simple. 3 minus 5, that's negative 2. Negative 2 squared is 4. I got 4 times a now. Well, if I got 4a plus 3 equals 0, I'm going to get the 3 to the other side and divide by 4. What did this tell us? If I have a equals negative 3/4, am I supposed to have this negative, or did I screw up? What?
Oh, because it's flipped.
All right, so I didn't screw up. If you look at yours and all of a sudden your a came out to be, let's say, 8. I'm looking at this graph. Does this look like it has a stretch factor, a vertical stretch factor of 8?
Really?
No, a vertical stretch factor of 8. Okay, better be, whoops, sorry, wrong way. Really skinny and going up. Okay, this right here is supposed to be a little wider, than normal. Okay, I don't know what normal is here, but it looks 3/4 isn't that far away from 1. Okay, and it is going down. All right, so with today's lesson here so far, on a scale of 1 to 5, where do we end up with today's lesson? All right. Okay. Your homework assignments. So just a second. I think, is that what you guys wrote for your formula there? You said to write the formula. Did you plug the negative 3/4 in there? Okay. Your assignment for tonight. Okay. You still got that little half sheet, that little sliver of sheet I gave you? All right. Your assignment for tonight. You can write this down wherever you like. The assignment. Okay. Section 2.1. It was a lot easier for me to write down 14 through 41 and have you realize you have done some of those problems already. And if you want to do them again, you have fun. Go ahead, do them again. Okay? Like I see 33 back there right now and 35 back there. I see number 20 behind me. Okay, so you figure out which ones you've done already and you can skip those. Okay, but I believe 43, 45 through 49, and 52, those are all new problems for you to do. Okay, so that is your assignment, for tonight from the book. Okay? Cindy?
Pulling out, but there's somebody following.
Hold on. Okay, we are actually going to get to that. Okay? Now, the second part of your assignment is you need to go on to the website. Okay, on that little half sheet of paper, that sliver sheet of paper, go ahead and write down this website. Okay, www.my.hrw.com. I think biology. Do you guys have a whole book for biology?
Yeah.
Okay, or had one? I don't know who has biology or had it. You already had a biology online textbook, and I just added to your little biology icon an Algebra 2 icon, so you click on the Algebra 2 icon now instead. Your password should have been the same, because I used your user information from your biology teacher. Okay? If not, this is what this little sheet's for. Okay, when you go to that website, it's going to say username and password. You're going to type in, right after your student ID number, is your username. You can write that there. This is my username. And right after that, some weird thing that I don't know, the computer generated your password. Now, that is a weird password. So if you want to write that down like in your phone in the notes, go ahead and do that right now, because I think most of you carry your phone around most everywhere you go, right? But I think this little sheet of paper is not as valuable as your phone. Okay, so I don't think you'll probably keep this forever, unless you put it in your wallet or on your purse. Okay, so if you have a phone, okay, or you have a planner, you know your daily planner, some of you carry that everywhere, put your username and password in there. I mean, this is not like your credit card username and password. It's not a big deal if it's found by someone else. Okay, it's just an online test. They can't do anything. Okay, so your continued homework assignment is this. Okay, you need to go to that website. You need to see all the components that are on that website, and then you need to email me 2 interesting facts, 2 interesting things you saw about the online test. If you don't have access to the internet at home, do it before school, after school, your study hall. Okay, get down to that library and do it here. Go to my lab right over here and get in there and do that. I need you to realize that you don't have to take your textbook home if you don't want to. Okay, you have that online textbook, all the problems are there, plus more help, plus Dr. Berger's video lessons, okay, plus additional examples, okay, as well as, you know, anything that you see from my website, right here, which you can know my videos are there, to email me. Does everybody know how to get to my website? To email me, here's how you do it. You go right down here at the bottom of it, and you click on feedback. You type in your name so I know who's sending the message. You type in your email address so I can send something back to you if I need to. And then your comments about what the 2 interesting things you have. Okay? Alright. Now, so that we can get a little bit of time here on your test.
I need to
Okay.
write my assignment down.
Okay? Does anybody need extra time on the test?
I need.
Okay? If you are in that boat, get a pen out right now, put your desk back into rows, come up here and get your test, and you got 6 minutes, okay, to do this. Aaron, do you need extra time?
Yeah.
Okay? You have to have a pen out. Okay, you got to do this in pen. I'm not guaranteeing what I'm going to give you, but you can do whatever you need to. Some of you are completely done. Some of you were not. Okay, Danny, Deanne, Sydney, Steve, Corey,
Yeah.
Nick. I'm not promising this will ever happen again. It probably will not. Okay, but I did it because I don't know the first time I ran a test and how long it's going to be, and I think this ran maybe 3 minutes too long. I'll give you 5. Nick, Albinia, Selena, Tim, Stasia. See, I'm still going to get it wrong.
Anastasia.
Abby. Lauren. Seth. Your last, Laura. Amber. Andrea. Honey, patched a couple pages. I'm not telling you to fix things. I'm telling you to go back right now and finish what you didn't get done. Okay, I'm not guaranteeing anything right now. What's in pen? Okay, if it's not done, if you're not doing it in pen right now, you just took a 0.
Why does it have to be done in pen?
So I can tell what you did one time versus the other. Okay? Now, last thing, you can listen and do this at the same time. If this homework assignment that you see right behind me is not done, you just took a 0 for your test. Okay, you need to make sure that you're doing this homework assignment for tonight. Okay, when I check it tomorrow, and I get that email tonight. Okay, otherwise you better get in here and tell me why you couldn't get to that website or you got in trouble.